Hello, thank you very much for watching my talk video. I'm Thomas Kesselheim from Bonn, and I'd like to present joint work with Marco Molinaro from Rio on Knapsack Secretary with Bursty Adversary. But as a matter of fact, I'm not going to talk too much about the Knapsack Secretary problem in this talk. I'll only do this at the very end, but I'll focus on the special case of the multiple choice secretary problem. The multiple choice secretary problem is a generalization of the classical secretary problem, which I guess many of you have seen before. Here we interview n applicants for k free positions one at a time, and after each interview we get to know how good was the candidate that we've just seen, and then immediately and irrevocably we have to decide whether we want to accept or reject this applicant. In the example on this slide here, we've just interviewed an applicant who has value 2, so probably we should reject them because we've seen much better applicants before. The next applicant has a value of 20, and well, this looks actually pretty good because it's better than anything that we've seen before. So let's assume we accept this. And if we now have only one free position, meaning if k equals 1, then we are done here because our position is filled and this decision is irrevocable, meaning that we cannot accept any of these later applicants, meaning we're missing out this applicant of value 52 and the one of value 80. So what is it that you can do for such a setting? What kind of an algorithm can you design? Well, it is pretty easy to see that if there is an adversary who chooses both the values and the order in which you see these applicants, this is completely hopeless. No algorithm will do better than the algorithm that chooses just k of these applicants randomly. But it is well known also that if still the adversary chooses the values, but then the order is random, then you can do a lot better. The classical result about the secretary problem is the following, that the expected value of the selection can be a 1 over e fraction of the optimum. This is known at least since the 60s for k equals 1, and this also generalizes to larger values of k. And for larger values of k, you can even do better. You can even get closer and closer to the optimal selection. What precisely do you compare here? Well, you compare the expected sum of the values of the applicants that you're selecting on the one hand to the optimum, which is now defined as also the sum of the values of the best k applicants. And the ratio between these gets now as good as 1 minus O of 1 over square root k. This is the optimal guarantee for this setting, which was shown by Bobby Kleinberg in 2005. Now, all of these results require that the order is random. They immediately do not hold anymore if at some point something unforeseen happens. And this is exactly what we were interested in. What if actually most of the input is in a random order, but here and there something that is defined by an adversary happens which does not follow the random order? To capture such settings, we introduced the following Bursty Adversary plus random order model. Eventually, we will have a sequence of items arriving one after the other, and all the values are chosen by an adversary, but the adversary can only partly determine the order in which the items show up. So how does this work in more detail? We first have an adversary who chooses which of the rounds are adversarial, an item for each adversarial round, and the set of items for all other rounds. So in my example here, the adversary may have fixed a value of 10 for the first round, of 1 for the second round, and so on. And the adversary still leaves some other items for the other rounds for which it does not determine their order, but only the set of items. Because this is what happens in the second step, then nature assigns these items randomly to the remaining positions in the sequence. So now we have a sequence which is partly adversarial, partly random order, which will then be shown to the algorithm. But it's important now to mention that the algorithm cannot actually distinguish between whether this is an adversarial round or a random order round. It just now sees a sequence of items arriving, and it just has to deal with the situation that sometimes this might be in random order, but sometimes it might also be coming from such an adversarial round. Unfortunately, so far the adversary is far too strong, and that's why we have to introduce some further assumptions. The first assumption is a burstiness assumption. This is required because so far the adversary could make just every round adversarial, and in this case this would be, we wouldn't have a chance. What do? Well, we partition time into windows of length L, and we now assume that only gamma of these windows may contain any adversarial rounds, and most of the windows should not contain any adversarial rounds. What may still happen now is that the adversary is presenting us valuable items only in the adversarial rounds and nothing of any value in the random order rounds, which eventually makes them as strong as presenting us a fully adversarial sequence. So this is something that we have to forbid some way, and the way we chose to deal with this is to change the benchmark. So we comparing ourselves only to the best k random order items. So whenever we want to guarantee something for an algorithm, the question is, how good are we comparing to the best selection of k items that appear in the random order rounds? With this modified benchmark, all existing algorithms that we were considering failed. And this is mostly because of the following difficult instance. In the first k steps, the adversary presents us exceptionally good adversarial items. This is, of course, covered most likely even by the very first window, and only then we see any random order sequence of items that have only smaller values. Let's see what's happening then at the example of Bobby Kleinberg's algorithm. This algorithm has the property that it does not pick anything at the very beginning of the sequence with high probability, because at the very beginning of the sequence it tries to get an estimate of how good items are. And then later in the sequence it picks only items that are among the top k items so far. Consequently, this now means that this algorithm doesn't pick any items with high probability on this sequence because, as I was saying, it doesn't pick these adversarial items because those are at the beginning of the sequence. And then later on, every item we are seeing is worse than these adversarial items that we saw at the very beginning. So we don't pick these either. You will observe similar things for other algorithms, which often use the first fraction of the sequence to estimate the optimum. And this is what can be easily fooled by an adversary by presenting you exceptionally good items at the very beginning of the sequence, and then you are far too picky to choose anything later happening in the sequence. The algorithm that we present in this paper is different because it tries to bound the effects of these adversarial bursts happening every now and then. How does it do that? Well, suppose we're in round T and we have to decide whether we want to accept or reject the current item. How do we do that? Well, we use the LP that you see here on the right-hand side to guide our decision. This LP is trying to infer what the random order optimum so far might have looked like. It exploits the fact that, well, this random order optimum is spread out evenly over all these random order rounds, just because we have a random order. So we have now seen some fraction of the random order items, and out of these, a fraction of this, a fraction that should be proportional to the fraction of overall items that we've seen so far, should belong to this random order optimum. And this is reflected by this first constraint. It says, okay, out of the items that we've seen so far, a fraction that is proportional to the number of random order items seen so far times k should be taken into consideration. Unfortunately, we haven't seen, we don't know which of the rounds so far were actually random order or adversarial rounds, so we have to estimate this. And our estimation that we're using here is this t minus 4 gamma L over n. And then you see the other set of constraints, which is kind of doing the same argument for every window. It says that each window will only get a bounded number of random order items in expectation, so also from each window only a bounded number should be taken into consideration when we're not trying to infer this random order optimum. And having now solved this LP, we take an item into consideration if it is at least picked fractionally by this LP, meaning that if its associated variable gets a positive value. But even then, we are not definitely picking it, but two more things have to be fulfilled. On the one hand, well, there's the constraint that we are not allowed to pick more than k items overall, which means we are only allowed to pick this, of course, if only k minus 1 items have been picked so far. That's clear. But then this other constraint captures that, well, actually it may still happen that we are now in an adversarial round and the adversary is trying to trick us. What are we doing now? Well, we just make sure that within every window we only pick a bounded number of items, a number of items which is proportional to the length of this window compared to the overall sequence and the respective k, so the number of items that we're allowed to pick overall. So for this algorithm, we can show the following guarantee. We can show that the expected value that we're getting from all random order rounds is at least some fraction of the random order optimum under the assumption that gamma is at least square root k and L is equal to n times ln k over k. Once again, what were gamma and L? L is the length of each window, and gamma is an upper bound of the number of windows that contain adversarial rounds. The way you should think about this is the number of windows that contain adversarial rounds. If this only grows sublinearly in K, then for growing K, you get closer and closer to the random order optimum. Or you can also consider the case that gamma is exactly equal to square root K, in which case you almost match the optimal guarantee of 1 over 1 minus O of 1 over square root K, which holds even in the case, which is optimal even in the case that there are no adversarial rounds at all. So, having spent quite some time now introducing the model, explaining the algorithm, this leaves me unfortunately only with very little time talking about the main part of our paper, which is proving this theorem and this way analyzing the algorithm. But let me try to give you a few high-level ideas of what we're doing there. And to this end, consider a time t that is in a window without any adversarial items, meaning this is a random order round that we're now talking about, and it is not too early in the sequence. What is happening then? Well, it may be that a good item arrives, in which case we should make sure that we accept this item, or a bad item arrives, in which case we should make sure that we reject it. Let's talk about the case of a bad item first. Let's assume that the jth best item arrives. We show that then the probability that it is picked is upper bounded by the term that you see here, which is exponentially decreasing in j. Why is this true? How do we show that? Well, up to this point, quite a number of items that are better than this one must have arrived, which comes from the fact that, well, there have been quite a number of random order rounds, and so by concentration also many of these items, many of these rounds must have had better items. And this means that the optimal LP solution that the algorithm is using can do without using this item. Then, using further concentration bounds, using the fact that at least in some way the random order rounds are independent enough, we can show that this implies that the algorithm stays within its budget with high probability. This then means that if a good item shows up and the algorithm wants to pick it, this is possible. So this is then still what we have to show in the second part, that a good item is likely to be picked. And this then we show with the following statement: if one of the best 1 minus epsilon times k items arrives, then it is picked with pretty high probability. To show this, we use more or less the same kind of an argument. For example, in this current window, it is pretty unlikely that many of these good items arrive. So that's why this one constraint from the LP doesn't hurt us here. Or also, in this current window, there are no adversarial rounds. So the adversarial rounds, they are in other windows, and they are restricted by the respective LP constraints. And this overall lets us show that, well, the LP optimum is most likely using this item, and that's why the algorithm wants to pick it, and it can do so just because we showed that bad items are not picked with pretty high probability. And this entire argument works although there are these adversarial rounds here and there. As you may have guessed from the title, our paper is not just about this multiple choice secretary problem, but it's about the knapsack secretary problem. In this problem, each item does not only have a value, but it also has a weight, which is some real number between 0 and 1. Our goal is still to maximize the sum of the weights of the items that we accept, but our constraint is now to ensure that the sum of the weights of the items that we accept is at most k. This is a generalization of the multiple choice secretary problem because you could recover that by setting the weights to 1 for all items, and then the constraint just means that you can accept at most k items. As a matter of fact, everything that I talked about in this talk generalizes to this setting. So the algorithm generalizes, you only have to include the weights in the LP and also in the other constraints, and then you're fine. And also the analysis generalizes. But there is one more thing that you have to take care of, namely, what does it mean for an item to be good or to be bad? And we do this as follows. We consider what we call the weighted rank of an item. Let me explain this quickly to you what this means. If you solve the fractional knapsack problem, then you can do this with the greedy algorithm. And this greedy algorithm picks items by decreasing value density, where the value density of an item is its value divided by the weight. The weighted rank of an item is now the fraction of the knapsack that has already been filled when we start picking this respective item. So this means the fractional greedy algorithm picks item I if and only if its weighted rank is at most 1. And by pick, I mean it picks it at least to some fraction. If now a weighted rank is 2, then it would only start picking the item if the knapsack was at least double the size. Using this weighted rank, you can do the exact kind of comparisons that I did earlier, meaning that you then can argue if an item is bad, meaning if it has a bad weighted rank, then it is unlikely to be picked, and if an item is good, meaning that it has a good weighted rank, it is very likely to be picked. Talk here. What did I show you? Well, I showed you a model that allows some adversarial rounds in an otherwise random order sequence, and I also showed you an algorithm that gives you good performance for the multiple choice secretary problem in this setting, which also generalizes to the knapsack secretary problem. What are interesting research directions from here? Well, one thing that we're frequently asked is, could you somehow include adversarial items into the benchmark? And as a matter of fact, I don't know yet. Maybe that is possible, but I don't have a good idea of how to do that. And more generally, you could ask, well, are there other models that somehow interpolate between this adversarial and the random order setting, including maybe some adversarial parts, some random order parts? And for all of this, we can also ask, does our algorithm work, or can our analysis be extended to such setting? Somehow I'm confident that our algorithm and our analysis can actually be extended to such settings, because I personally feel our analysis is pretty strong, and so that's something that one might have a look at in the future. So thank you very much for your time watching this video. If you have any questions, please feel free to send us an email, and let's hope to meet in person again soon. Bye for now.